Okay, great. So at the end of last class, we touched on issues about purity versus mixedness of a state and started talking about entanglement. And so now let's do that more systematically. Okay, so just to recap, last lecture we saw two situations for which a more general notion of state, description, or model of quantum states. Remember, you should think of quantum states as modeling preparation procedures to avoid any metaphysical commitments about what that means, what the quantum state means. So last lecture, we saw situations for which we saw, two situations for which a more general description of quantum states was needed. So those two situations being one where you just have a device which is classically, probabilistically mixing different pure state preparations, and another where you imagine a composite system which is somehow prepared in an entangled state, but then you're only interested in describing one of the subsystems. And in both of those scenarios, in both cases, the most general mathematical model was, how do I say this? The most general mathematical model well, maybe model is a bit of a strong word. Let me call it representation. Needed was the set of non-negative linear operator rho, and if we're going to follow the normalization convention, the probabilities add to 1, then we want the trace of that operator to be 1. And then I mentioned how what was remarkable was that given give me mathematically some non-negative linear operator of trace 1, it turns out I can always realize that experimentally or operationally, either via taking mixtures of pure states or by preparing an entangled state in a composite Hilbert space and tracing out the other system. So it turns out any element of this set can be realized in both of those paradigms, those operational paradigms. So then I mentioned there are three equivalent characterizations of purity. So one was that rho was equal to a projector for some psi. Two was that rho squared, that rho is idempotent, so it squares to itself. And 3 is the condition that the trace of rho squared is equal to 1. The more general way to say this is actually trace rho squared is equal to trace rho. And then trace rho is equal to 1 if we're following the standard normalization convention. And I mentioned also how this condition seems to be weaker than this, but because we impose the condition of non-negativity on this operator, it turns out that this condition it actually implies this. Yeah?
So, I don't from last time, but is this what we take as the definition of a pure state?
Yeah, a pure state can be defined by any of these three. I mean, the way we defined it in the axiom was condition 1. Right? I said that you have a projector. And now I'm saying that these other two criteria are actually equivalent. Under the assumption we're talking about a density operator. So I should say, given a density operator, there are 3 equivalent characterizations of pure states. Okay, so now we had our ideal axiom said that our preparations were given by rank 1 projectors, and now we have a operational axiom 1. So if we're talking about kind of the fundamentals, we're talking about the wave function of the universe, say, or something like that, then we're happy with ideal axiom 1. If you want to talk about some system you've prepared in a condensed matter state, condensed matter system, or in a some ion trap or a superconducting qubit or whatever your system is, an atom in a cavity, and you want to say what can I find experimentally? What is the class of mathematical objects that describes the possible set of preparations? Well, then we were going to generalize rank 1 projectors to mixed states. To density operators. And so what was my wording for axiom 1? It was something like the ideal preparation of a quantum system. So let me say that. So the practical characterization of a the practical preparation of a quantum system is described by a density operator. So I'll put a symbol with it. Now, I defined density operator previously as being a non-negative operator with trace 1, say. Okay, so I meant to mention here that, sorry, I forgot to mention something. So if I give you some matrix and I claim it's non-negative, I promise that to you, and I say, tell me if this preparation is pure or not, the easiest thing to do is just calculate this, multiply the matrix with itself and then take the trace and check if it's 1, assuming I'm following the standard normalization convention. So this is the easiest thing to apply in practice if you have a mathematical problem. And then, so I'll just mention here that trace rho squared is bounded above by 1 and bounded below by 1 over the dimension. So you should always get an answer in this range where saturating the upper bound means you have a pure state. Saturating the lower bound means you have a maximally mixed state. So the identity state, you can trivially check that you get 1 over d for that case. So in some sense, this is a monotonic measure of how much mixedness you have. It's a measure of your lack of knowledge about the actual preparation, about some pure preparation. And so I'll just mention a theorem. So any density operator this is what I said earlier, can be expressed as a convex combination of pure states and another theorem is that any mixed state, well, I guess I haven't, right. So if a state is not pure, then it's mixed. Any mixed state admits an infinite number of such decomposition. Well, I won't say such, of convex decompositions. Well, what I mean is this, is infinite number of, I'll just say such, of such decompositions. So a pure state has only one such decomposition, this one, and a mixed state has an infinite number of such decompositions, and this is called the ambiguity of mixtures. So a trivial example of this is if I give you the identity, if I give you a system prepared in the identity state, then you don't know if I prepared it by preparing spin up with probability half and spin down with probability half, or if I prepared it with spin right with probability half and spin left with probability half. That's empirically impossible to determine. And that this is different from class. Now, I've been emphasizing the similarities between quantum states and classical probability distributions, so this is a difference. All right, so this is different from classical probability theory. All right, so traditionally if I have, let me just finish this thought and then I'll take some questions. So in classical probability theory, the space of probabilities is described by a simplex. So here I can draw the two simplex. So here I have three events. So I have, a three-sided die. I guess that's impossible, but some three outcome situation. So this is outcome, say, 1, 2, and 3. And then the way it looks is this. You draw your three-dimensional, so this is R3 now. And then this axis is the probability of outcome, it's called P1, P2, P3. Here, I'll call this P1 for consistency. And so this triangle is the two simplex, and the way it's embedded in real space is this. You have this kind of triangle laying on its side against our three-dimensional axis system. And so the set of probabilities is the surface of this triangle. And so if I prepare the system with certainty to have outcome 1, then it's this probability distribution at this point here. And certainty of outcome 3 is this point here. But if I have if there is 50% probability of outcome 1 and 50% probability of outcome 3, then I'm on this line right here. If I have some finite probability of P2, that's going to bring me towards this point, and I'll be somewhere on the surface. So the point is, any mixed state, which is a point away from these extreme points, a mixed state classically, corresponding to not certain knowledge, admits a unique decomposition in terms of these three extreme points. So the problem is, in quantum mechanics, we have a different situation. So I would have been stressing to you that there's this deep insight to be gained by thinking of quantum states as probabilistic objects. And now when you do that, what becomes interesting is now how does quantum mechanics differ from that picture? And then we're starting to understand something truly quantum. And here, this is an example of it. So I should just say this. Any probability vector admits a unique decomposition. So classically, any probability vector admits a unique decomposition in terms of the pure states. So by pure states, classically, I mean the extreme points. Extreme points of the simplex. All right, there were a few questions. Well, there was a couple of old ones. Did you want to?
Just clarification. What you mean by convex combination is just non-negative coefficients that sum to 1? Okay.
Yeah, convex combination. The question was, what precisely do I mean by convex combination? I mean a linear combination with non-negative coefficients that sum to 1. So a probabilistic combination is a convex combination.
So you said that the trace of rho squared is a monotonic measure of the mixedness?
Yes.
So monotonic with respect to what?
Yeah, that's a good point. Let's see, does that make sense?
What does it have to do with monotonic?
Unitary evolution is fixed.
Well, it's going to be monotonic, actually, okay, it's going to be monotonic with respect to the von Neumann entropy of the state. So the von Neumann entropy, in some sense, which I'm going to get to, by the way, is going to give us a kind of an operationally motivated ordering of states based on our lack of knowledge, because it's a measure of uncertainty. And then generally, that's going to be, I'll describe it in a minute, that's going to be hard to calculate because it has a log in it. So trace rho squared is like kind of it's like a cheap way to calculate it.
The Neumann entropy is not monotonic, is it? I mean,
With respect to what?
I mean, if you take different states and you calculate the Neumann entropy, it's curved like this. So how are you going to?
No.
No, that's yes.
No. It only defines a partial order on states, not a full order, but it's coming up. So let's postpone answering that until we.
I had one more question. So you said that the difference between quantum and classical is that you can have these. You don't have a unique quantum decomposition. Is that just equivalent to the statement that it makes sense in quantum mechanics to talk about superpositions of basis states, but classically it makes no sense to talk about 1 over root 2. You rolled a 6 and you rolled a 3.
You know, it might be related. So the question is, does it relate to the idea of superposition? So, you know, maybe in some indirect sense, I think that's a correct insight. Let me flesh that answer out a bit. So, it turns out that you know, I've been emphasizing we should think of quantum states as probabilistic states, and we should think of quantum states also as states of incomplete knowledge. So that means my maximal knowledge achievable about a quantum system, which means I can define a pure state associated with it. That's my maximal knowledge. And so what I would argue is that maximal knowledge is incomplete knowledge, either about the outcomes of future tests or about the underlying reality, depending on your tastes. And the interesting thing you can see when you look at classical probability theory is if I impose an epistemic restriction on my simplex. Suppose I say, for reasons which I don't know what the mechanism is, for some reason I have some classical system for which I'm unable to reach the extreme points. So I define my set of accessible probabilities in describing whatever it is. I can have a box with 3 holes, and I can have a ball in one of those 3 holes. And I have a machine that drops the ball in. There's a probability of it falling in one of these 3 holes. Suppose that machine is such that it has some intrinsic randomness, so it's actually never going to happen that I have certainty about it being in some hole. There's always some finite uncertainty that it'll be in some other hole.
So you're talking about now about a whole set of machines of this sort?
No, I'm just saying, so there is a machine, I press a button, it drops the ball in the hole. The ball is always in some hole. I repeat the experiment thousands of times, and I guess what's the probability of finding it in hole 1, the probability of finding it in hole 2, the probability of finding it in hole 3. Suppose that the machine is dysfunctional, and so even though I wanted to put the ball in hole 1, it always has some finite probability of missing hole 1 and putting the ball in hole 2. So in other words, the maximal knowledge I have about the preparation, because of this machine, the way it functions, is not perfect knowledge. So I can never, if I know the reality of this machine is that it never puts the ball with certainty into one of the holes. All right, so I'm just imagining some ad hoc situation. The point is, if you have that situation where maximal knowledge classically is not complete knowledge, which corresponds to okay, I have no idea what I'm doing. Then here, I'll just go over here. So this is an aside. So here's my simplex. If I'm describing a situation where I can't have perfect knowledge, classically due to some constraint, then what I have to do is I have to chop off the extreme points in some way. And I say my accessible space is this subset of the simplex. Then you get something really interesting. What you get is that if I have a mixed preparation, now in terms of the extreme points of my new set, there is a non-unique decomposition now. So what you see is that if you extend this conceptual analogy to, well, look, I have a physical situation where maximal knowledge is not complete knowledge, then I'm deviating from classical probability theory, which always allows perfect knowledge in principle. And I'm describing a special situation where I'm actually unable to achieve perfect knowledge due to some constraint I'm unaware of. Then it turns out you reproduce the ambiguity of mixtures.
So when you say maximal knowledge, in this case, you mean knowing exactly where in the simplex your probability distribution is?
Maximal knowledge in this setup is what's achievable in practice. So in practice, I can only know my knowledge is represented by a point in this space. Complete knowledge corresponds to saying my point is here, here, or here. I know with certainty where the ball will be. If my maximal knowledge is not complete knowledge, that implies there's a gap between complete knowledge and the maximal knowledge I can achieve about that system. So here, this boundary tells me I'm in a contrived scenario classically where maximal knowledge is not complete knowledge. And then when I imagine that contrivance, then I end up reproducing a huge, even a larger fraction of quantum phenomena than I could have reproduced just by looking at classical probability theory in its purest form. And so this point has been illustrated the best probably by Rob Speckens. Rob Speckens, what's known as his toy theory. And I have a paper coming out also with my students. So this toy theory is for qubits. And he adopts this kind of a principle that maximal knowledge is not complete knowledge. And he shows that a huge number of quantum phenomena fall out of that simple toy model, even though it's just a classical model. And then we can generalize that to any power of odd prime. So I'll just, I'll just say it's my group. So we haven't written the paper yet, so I don't know who's going to be first author yet. But so Emerson forthcoming, Emerson et al. Forthcoming. We look at this in the case we have such a model for all odd dimensional systems. For all odd dimensional quantum systems. And in this model, you have quantum superposition in this classical model. You have things like quantum teleportation. So it's not really quantum teleportation. You have an uncertainty principle. You have a no cloning principle. You have ambiguity of mixtures. There's a lot of stuff going on in this model that's quite remarkable. So in some sense, I think the one thing that's unique about these models is they have a notion of quantum superposition. But what they don't have is they don't have a distinction between coherent and incoherent superposition. So quantumly, I can have alpha 0 plus beta 1, a coherent superposition. And then you say, what's the probability of outcome 0? Well, it's alpha squared. Probability of outcome 1 is beta squared. I can also write down a state, modulus alpha squared projector onto 0, 0 plus modulus beta squared projector onto 1, 1. And that's a mixture of 0 and 1, which has the same empirical probabilities of outcomes 0 and 1 as the coherent state. So what I'm getting at is that these models do not have, you don't have both coherent superposition and classical mixing. You just have quantum superposition in some sense. That's a nuanced point. Let me just retract that. But what you were asking at is kind of addressing some of the nuanced issues in this model. So maybe we should talk about that offline. All right, there are quite a few questions in the back.
Clarify, if we have a state that's a statistical mixture, there is a unique decomposition.
Yeah.
If what?
If we just have a state that's a classical statistical mixture of states,
Yes.
there is a unique decomposition.
Yeah, that's what I said right there. That's what it says. It says classically there's a unique decomposition in terms of the pure states, which is the extreme points of the simplex. But what I was saying here was that when you say that you can't reach those extreme points, then you get an ambiguity of mixtures classically.
I guess I meant even if you have a quantum system that is a statistical mixture, there's no difference between that and a...
No, then there are unique infinite decomposition.
If you have a density matrix, you can decompose it however you want.
There's one that's the true one that was how it was produced, but it could be decomposed in other ways.
So this fact that you can decompose it in infinitely many ways, it's like justifies that you have to choose an ensemble of probabilities and quantum states to have a unique decomposition of your density matrix.
Well, you can choose a preferred decomposition, but it's not going to be unique. Is that what you're getting at? I mean, there always exists some preferred.
If there's an ambiguity of mixed states, then which one do you choose?
Well, that's the point. You can't. You don't.
I can choose anyone.
You can choose anyone you want.
How?
So the point is this. The verifiable predictions of quantum theory are based on the Born rule, which is based on the trace of rho against the measurement. Decompose rho however you want, you're going to get the same predictions. So you experimentally can't distinguish between different choices of decomposition because they produce the same observable probabilities. Emily?
Is the reason that you have infinite decompositions in the system just that you've now given yourself an infinite basis? You no longer have a finite number of extreme points.
No. This is finite dimensions. So this is a qubit.
When you do this, when you cut off the extreme points.
Oh, in this model. Yeah.
Infinite extreme points.
Yeah. Is that true? I don't know. I don't know the answer to that. I don't know if you impose the constraint. I mean, here I have a curved surface because this is what we actually get in our model. But if instead of this kind of boundary, I did something like this, then I would have a finite number of extreme points, and I think I would still have the ambiguity of mixtures. But I'm not sure. But so that's an interesting question. Yeah.
I think this is already asked, but so there is a preferred decomposition. So say if I'm like spitting out atoms from like a thermal bath or something, and I can weight them, the energy eigenstates by like Boltzmann factors and stuff. So that would kind of be the natural choice, but I could also decompose that in an infinite number of other ways.
Right. So there's a natural choice based on your understanding of what's happening inside the box.
Okay.
But what I'm saying is if that box spits out a system and someone can press that button 1,000,000 times, someone who's not you, who doesn't know what's going on inside the box, they have no way of knowing.
So I would be able to tell it.
Yeah, so there's a preferred one based on the physics of the situation. So that's true. But mathematically, there's no preferred one.
Okay.
Good. Did we exhaust the questions about that topic? All right, so now let's talk about criteria for entanglement. So first thing we're going to do is we're going to assume the state is pure. Okay, so I'm going to tell you what we know, tests for entanglement. They only work when we assume the state is pure. So don't forget this assumption. So that means our rho, which is a linear operator on H, because we assume it's pure, we have that rho is equal to a projector. Let's call it chi. Okay. Then rho A this dangerous thing here. Get this out of my way. Then rho A, defined as the trace over B of chi chi, is not pure. So the trace of rho A squared is strictly less than 1 if and only if chi is entangled. Or let's scroll here. Chi chi is an entangled state. Okay, so I alluded to this last lecture that basically, remember, how do we prove this? All right, so proof. All right, suppose we're going to do a proof by contradiction. Suppose chi is pure, unentangled. So there exists a psi in HA and a phi in HB such that chi equals psi cross phi. Then rho A is equal to the trace over B of chi chi. And now when I evaluate the partial trace, I'm summing over a basis for HB. Let me choose a basis that includes phi as one of its orthogonal elements. All right, then when I evaluate the partial trace, the first element is phi itself. This gives me 1. The rest of the elements are orthogonal with phi, so they give me 0. So then the trace over B is equal to a sum over L, phi L, chi chi, phi L, where here, L goes from 1 upwards. Let phi 1 equal phi itself. then phi L not equal to 1 against phi is equal to 0 by orthogonality of the basis. Hence, rho A is just equal to psi psi. Okay? And then it follows that trace of rho A squared is equal to 1. Okay, which confirms purity, although of course that's redundant with this statement. So yeah, so it's a very simple way, it's very simple to see this. And you can also see what's going to go wrong now is if my state is mixed, then this test won't work, right? So this test does not work if rho is a mixed state. So for example, let rho equal psi psi cross let rho equal sum over L psi L with some probability PL cross, whatever, phi phi. Then rho A is just equal to sum over L PL psi L psi L. So in general, trace of rho A squared is going to be less than 1, but there's no entanglement between A and B. Okay? Is that pretty straightforward? Okay, so let's talk about the degree of entanglement. So there is a distinguished measure of the degree of entanglement for pure states. Again, I'll let you know when I stop assuming the state is pure. So here we're still working under this condition, our standing assumption. So the standard way to quantify the degree of entanglement for pure states of A and B, the von Neumann entropy is distinguished. Is a distinguished measure of entanglement. And so this entropy S of rho A is equal to minus the trace of rho A log rho A. Here we'll work in bits, so we'll make this log base 2. Oh, and I should mention everything I'm saying here about rho A, everything is symmetric with respect to exchanging systems A and B. So I can equivalently have stated all of these statements in terms of B. So I could have traced out A and looked at rho B, and all these conditions would apply. All right? So that should be obvious from the setup that there's nothing special about A versus B. So remember the minus sign here. And here you have to be careful with the meaning of the log. So what do? We take the log of 0 to be 0, I think.
0 log 0 is 0.
Yeah, we define, 0 log 0 is undefined, but we define it to be 0. All right, so how do you calculate this, right? So this is something you may have seen, but okay, let me just mention, recall that if we have an operator A for any linear operator, well, I shouldn't say any linear operator, for any normal operator, which is therefore diagonalizable. So this will include states and observables, preparations and observables. A, we define f of A as, so one way to do it is a Taylor expansion. Another way to do it is via spectral decomposition. So we define is equal to f of AL. So you just apply the function to the eigenvalues. And that defines the function of the operator. So in this way, so here's our spectral decomposition for A. Then we wanted to talk about a function of A. We can just apply that function to its eigenvalues. So this is true if the function, if A is a Hamiltonian and F is a unitary, so e to the IHT. This is true if A is a state and the function f is the log. Just take the log of the eigenvalues. Now remember, a state that doesn't have full rank will have 0 eigenvalues. Right? That's clear? So if it has 0 eigenvalues, we have to define what 0 log 0 means, because it's undefined. So we just define that to be 0. Okay, so this is our von Neumann entropy. And it's going to give us a degree of entanglement. So we have that S of rho A is bounded above. Well, rather than do that, it's always better to follow the notes and start going flying off the cuff here. So let me just stick with what I'm doing in the notes. I have a nice ordered list. So properties. We have property 1, S of rho A equals 0 if and only if rho A is pure. 2, S of rho A is lower bounded by 0 and upper bounded by the log base 2 of the dimension. So here we take rho to be an element of the linear operators on a d-dimensional Hilbert space. Then we have log 2d. And the upper bound is saturated if the state is the mixed state, identity over d. I have one more property. I have 2 more properties. Okay, so again, if rho is pure, then S of rho A is equal to S of rho B. That's the symmetry condition I was mentioning earlier. And then fourth, it's concavity. Which is that S of sum over I, Pi, rho AI is greater than or equal to sum over I, Pi, Pi,
S of rho AI.
So let me just say that I'm stating these conditions in terms of row A, but really this is true for just any row, right? Any row. All right, there were some questions. I think there was one here first, yeah?
Can you just remind me what properties normal operators have? Like why are we using normal operators instead of Hermitian?
Just to be general?
I mean, just
Because a unitary operator is not Hermitian.
right.
Traditionally, a unitary operator is e to the IHT, right? So there, we want to talk about the ability to diagonalize a unitary, even though it's not Hermitian. So the normal operators is the biggest class that's diagonalizable.
And orthogonally that.
Orthogonally?
Like, I mean, they have an orthonormal basis of eigenvectors.
Yeah.
Okay. And are their eigenvalues necessarily real?
No. They can be complex.
Cool. So that's the only difference.
Like a unitary, basically.
Okay.
Yeah.
Various questions. First, the one is why do you take the Neumann entropy to be a measurement of entanglement? I mean, I can make the classical analog to the amount of information that you can have from a probability distribution, which is Shannon's entropy, right? Which is exactly this.
It's Shannon's entropy of the eigenvalues. The von Neumann entropy of a state is Shannon entropy of the eigenvalues.
So somehow entanglement is the amount of information that you have from your subsystem?
It's a measure of ignorance. It's a measure of how spread out the state is across some orthonormal basis of its eigenvector, of the rho in general. The point is, in general, you have rho is expressed as any rho can be expressed as a convex combination of some projectors and some choice of basis. So if you're pure, it means that P1 is equal to 0 and Pi not equal to 1. Oh, sorry, P1 is equal to 1, Pi not equal to 1. That's a pure state. The more uniform this probability distribution is over this orthonormal basis, the less knowledge you have about the outcomes of experiments. Any experiment, guaranteed. All right, you have strictly less information as this probability distribution becomes more uniform. And so that's an operational criterion for why this is a good measure of ignorance. But what I haven't answered is, so definitely I think it's clear that the von Neumann, it should be clear that the von Neumann entropy is a good measure of ignorance. If you know how Shannon entropy works, then that's one step. The next step is, why is it a good measure of entanglement, right? Why is that? And there's a very good answer to that question.
The other thing, that condition that S of rho A is equal to S of rho B is just for pure states, right?
Repeat that, please.
The Neumann entropy of rho A and rho B they are equal only for pure states, right?
Only if the global state is pure. So rho A and rho B are derived from only if the rho on HA cross HB is equal to a projector onto chi, some projector, then that statement holds. So when I said if rho is pure, here I didn't draw, there's no index on rho because rho refers to the global state.
Okay, so if let's say I don't know anything about von Neumann entropy, right? And the definition of being entangled or not, if your pure state is a product state or it's not a product state, right? So what do you mean by a degree of entanglement? How can I have an intuition over that?
Yeah. So first, let me make precise my claim about ignorance, and then I'll describe why it's a good measure of entanglement. Yeah.
And one more question about the properties. Where are those PIs coming from in the concavity property? Are those the PIs in rho?
Here? Here? Oh, just take some states and this result doesn't really fit into our discussion about entanglement. It's just I want to talk about the entropy of some state. What do I know about it? Well, if I know the state admits a decomposition in terms of other states, then I can bound the entropy of that state by the convex combination of the entropies of the constituent states.
Oh, okay.
So, yeah, it's a bit of it's kind of more of like an interesting fact that doesn't really fit into the entanglement discussion. So I agree this was a little bit unclear. So just here, let's call these remarks. The von Neumann entropy is a measure of our ignorance about the preparation. Here. Let sigma be some density operator so we have some density operator sigma, okay, so or rho, whatever, on some Hilbert space. Then von Neumann entropy is a measure of our ignorance of the quantum state sigma, of the quantum state. Okay, so in particular, S of sigma is equivalent to the minimum Shannon entropy over the set of probability distributions induced by all choices of measurement. Okay, so what I mean by that is that, look, given some state sigma, I can define some measurement. Born rule says the probability of outcome k is equal to the trace of sigma versus some projector, where we imagine some observable A is equal to sum over k, ak pi k. So now I can vary over all possible choices of measurement. Each one via spectral decomposition is some set of projectors. Remember the histograms I drew? If I have some preparation sigma, then that induces a histogram of outcomes. Where each of these k's indexes some outcome, and then I have an infinite set of different probability distributions I'll get depending on the infinite set of choices of measurement I can perform. Minimize the end. So, would anyone like me to remind them what the Shannon entropy is? Okay, the Shannon entropy. The Shannon entropy is a classical concept of huge relevance to information theory. The Shannon entropy of a probability distribution pk is what's the traditional symbol? Is it S? H, thank you, that's right. H of pk is equal to the sum, I think minus the sum over k of pk log 2 pk. Okay? So I told you that the von Neumann entropy is minus rho log rho. It's actually equivalent to, diagonalize rho evaluate the Shannon entropy of its eigenvalues, and that's exactly what the von Neumann entropy is. That's a mathematical equivalence between the von Neumann entropy and the Shannon entropy. There's an operational equivalence, which is that the von Neumann entropy corresponds to, so remember, H is a measure of the ignorance of the probability distribution. So if I have a flat probability distribution over outcomes, H is a maximum. If I have complete knowledge, so my probability distribution is one of the extreme points of my simplex, then H is 0. So H measures, so this measures degree, measures lack of knowledge or degree of ignorance. So bigger H means more ignorance. So you don't know which outcome you'll get. You're less and less certain about which outcome you'll get in any given run. Consider all possible measurements I can perform on this state. Choose the measurement where the probability distribution is least uniform, meaning that I have the least amount of ignorance. So that's the most predictable measurement I can make on the system. And that's what the von Neumann entropy of that state is. And of course, which measurement is going to give you the best ability to predict the outcome? Measure in the eigenbasis of rho. So that's the connection between the mathematical fact and the physical fact. So your optimal measurement, where you can predict with highest certainty what the outcome will be, is to measure in the eigenbasis of the state that was prepared.
So, I mean, in that line of thought, shouldn't the von Neumann entropy somehow refer to how mixed the state is? I mean,
yeah, exactly. That's exactly what it does.
Okay, but then how can it relate it to entanglement? Because this property you have here.
Okay, then. Patience, grasshopper. This is where we're going. All right, so now why is this a good measure of entanglement? So it turns out, and the proof of this is extremely involved, so I'm afraid I can't provide it for you. But there's a very rich way to think about entanglement operationally, which is the resource theory point of view. So the idea of the resource theory is that I want to think about these objects as resources, like money or food, and the idea is that we can exchange these resources. So I'll trade you 10 bananas for your 1 chicken. They're both resources. So now we think about entanglement as a resource. It's something people want, and so I have a factory which produces some states which I claim to be entangled, and I have a consumer who wants to buy those states, and then they say, well, you're preparing your qubits in some state which is entangled. I'm interested in pure Bell pairs of these 2 qubits. Okay, so suppose, okay, so here, let me just give a title to this. Y is S of sigma a useful measure of the degree of entanglement. Okay, so basically, there's kind of an ideal entangled state, and we introduce that as an assumption that the ideal entangled state is a Bell pair for 2 qubits. So for example, for 2 qubits, we take the singlet, psi minus. We could choose any Bell pair. We're choosing psi minus by convention. It doesn't really matter. Choose psi minus, which is 0, 1, minus 1, 0. So this is the Bell singlet. This leads to a maximal violation of Bell's inequality. So it's a measure of the degree of non-locality as well, but we'll get to that later. Entanglement and non-locality, we now understand just within the past 5 or 6 years to actually be distinct concepts. And so hopefully we'll touch on that before the end. That's really interesting. But anyways, so it turns out talking about entanglement, talking about non-locality is actually 2 different things, although traditionally they've been associated with each other. So here's the Bell singlet. And then now you have a factory that produces some state sigma, and you want to measure, well, how, and then your chief engineer comes to you and says, I can compare this state sigma, and your other chief engineer comes to you and says, I compare this state sigma prime. Our consumers want us to give them singlet states. So which is better for that purpose? So the question is a question of the distillation of singlet states from asymptotically many copies of sigma, the rate, let me say this, the rate of distillation of singlet states from asymptotically many copies of sigma, well, here sigma, remember, is a density operator. Okay, so let D of HA cross HB, let's define that symbol to mean the set of density operators. So these are non-negative operators with trace 1. So I don't have to write this out every time. Okay, so it's just an aside. So the question is, so now, of course, now we choose HA equal to HB equal to C2 for purposes of illustration. Okay, so we're talking about 2 qubits. And then you can ask, I have access to unitary transformations. I have a factory that spits out zillions of copies of this mix, of this state sigma of pairs of qubits. So I have 2 zillion qubits and a zillion pairs of okay, zillion is not a real number, but it's it's asymptotically many is what zillion means. So I have a zillion pairs of qubits, and my task is how many, by applying joint unitary transformations on that huge Hilbert space of a zillion qubits, a zillion bell pair, a zillion entangled state, a zillion copies of sigma, where sigma is a joint state, how many bell pairs can I extract? So I want to push. What I want to do is I want to take sigma cross sigma cross sigma cross sigma. Well, let's say I have n copies. Okay, so this is equal to sigma tensor n. Okay, so what Hilbert space does sigma tensor n act on? Yeah, so sigma tensor n is an element of density operators on H C2 cross C2 tensor n. So I have n copies of these pairs. Because remember, each sigma is acting on 2 qubit spaces at the same time. So the question is, how many? So what I'm going to do is I'm going to apply some transformation, and I'm going to take sigma tensor n. So apply a transformation that takes sigma tensor n to psi minus tensor m tensor junk. Okay, and these junk states are going to be, there's going to be n minus m copies of them, and they can be anything. I don't even care what they are. Okay, I'm going to throw them in the garbage. So the question is, how big is m? How many pure bell pairs can I extract? And then these bell pairs can be used, right? I can do teleportation protocols. I can encrypt bit strings with QKD. I can do all kinds of things with them. So these are a useful resource. Okay, and so you want to maximize m. And so the point is, people have proven that the von Neumann entropy of sigma uniquely determines the ratio of m to n. So
Is that true for any dimensional system?
you need an appropriately defined analog to the Bell singlet. So you need a maximally entangled reference state, which usually can be picked out uniquely, and then this works. So in general, not just for qubits, but in general, so this is Plenio and Virmani. So this is 2005, which wasn't that long ago. In general, the von Neumann entropy of a state sigma essentially gives the optimal rate of distillation. And it's the unique measure of entanglement satisfying kind of reasonable assumptions.
So what's wrong with the entanglement of formation?
What's wrong with it?
Well, what? It's not the same as
No,
entanglement
no,
entropy, is it?
right.
What-
No, I think, well, no. So, okay, so this is a very rich area of research, and there's probably 100 papers on this topic in the past 10 years. So there's a lot to think about. But to answer your question, for pure states, the two are equal, distillation. But for mixed states, there's a gap. And then, so for mixed states, it's less clear what, it turns out the right way to measure the amount of entanglement for mixed states depends on what task you're trying to achieve. So you're right. But for pure states, it's unique. But so what I just wrote here applies to mixed states. Oh, I can't raise this board. Sorry about that. Okay, let me just tell you what this says for those of you in the front row. So basically, the von Neumann entropy of a state sigma, including mixed states, sorry, for pure states, it's the optimal rate of distillation. And sorry, for arbitrary mixed states, it's the optimal rate of distillation. And in the resource theory framework, it can be identified based on some reasonable assumptions as being a unique or distinguished measure of entanglement. But as Emily pointed out, what measure of entanglement you're going to use, it depends on, for mixed states, depends on what task you're trying to achieve, what you want to use the entanglement for. So von Neumann entropy is a distinguished measure, but it's not the only measure you would consider. Okay? You look skeptical.
Yeah.
Let me just.
I know that the amount of copies that you can get of Bell states depends on the von Neumann entropy, right? But that doesn't make. I mean, for me, it's still unclear why does that measures your degree of entanglement. And even more if you are defining your best state to be an ideal entangled state, what does it mean to be an ideal entangled state?
No, that's an assumption. You just assume that somehow there is a pure state which is maximally entangled. It turns out that that's non-unique. There's many pure states.
Maximally entangled with respect to the Neumann entropy.
Yeah, okay, so I mean, this is a nuanced thing. So, I agree that there's something suspect about, like, if you read Plenio's paper, they say, look, we're just going to assume that this is a natural thing to do, assume that there is a maximally entangled state and that that's well defined. And then from there, they build their resource theory, which identifies von Neumann entropy as one of the distinguished measures of entanglement. But it is, maybe it's not fully satisfactory, the situation.
Somehow the only thing that I can see is that if the von Neumann entropy is different from zero, you have an entangled state, right? How can I make this a measure that characterizes states as this is more entangled than this?
Well, I mean, you start out, look, you can start out by saying, I'm trying to remember how this works now, but you can start out by saying, look, I'm interested in distilling bell pairs, and I assume I have a pure state, and then it's clear that what is the state that maximizes the rate of distillation? So you're distilling to a distinguished state, right? So you pick out what is the state you want to reach, right? So your target state is chosen by convention. Whether there's some clever way to distinguish that target state, I don't know. I mean, maybe someone's figured that out, maybe not. But it's so plausible, but I don't see grounds for doubting it. I mean, it's hard for me to imagine how the Bell state would not be, by any reasonable criterion, the most entangled state.
One thing that this one says that entanglement shouldn't be able to be increased by local operations on separate systems. And so, but you can show that the von Neumann entropy can never increase
Right.
that kind of
Okay. That's something that the von Neumann entropy does.
Yeah, von Neumann.
But I mean,
So that's one
But-
indication that
Well,
that's
entanglement
one
is a
type
word,
of-
right? Like,
But also trace row squared. Trace row squared is also that way. So there's lots of measures of entanglement which are non-increasing under LOCC. But okay, so for those of you who are interested in this topic, I'd suggest reading the paper. I'm not an expert on all of the different. I mean, this isn't the unique paper putting forward a resource theory point of view for entanglement. It's a cottage industry, and I haven't read the full literature on it. So I'll defer to those of you interested in this topic. This is a great paper to start, and you can find lots of other papers to explore this topic. It is a very deep topic. People do entire PhDs just on this topic. Okay, so there's a huge amount of knowledge out there about this, which we're only scratching at. Okay, well, I want to talk about the Schmidt decomposition, but I've run out of time, so I guess we'll do that next class and leave things here. Okay, great. Thanks for your questions.